Welcome to DCL 301. 301 is the beginning of a series on modulation. Now, the idea of radio is to send information over the radio wave. Modulation is the act of placing that information, whether it's human voice or whatever, on the radio wave. There are many modes of doing this, and in this video, I'll talk about CW and AM. So let's start with CW. CW means continuous wave. In amateur radio, CW means sending Morse code signals by radio. Something I won't spend a lot of time on, but I should explain this first. Back before 1910, we didn't have fancy things like tubes and transistors, and the only way to generate RF energy was with a spark gap transmitter. When you hit the telegraph key, a great deal of voltage was induced in the induction coil, and this rise in voltage would excite the tuned circuit on the right. When the voltage got high enough, the gap would arc. This arc would create repetitive voltage oscillations to the tuned circuit, and the tuned circuit would convert them into RF energy. This was a very rough, unstable, noisy way to generate RF. The waves it produced didn't last very long, so you needed a lot of sparks because the waves were damped. They would start out strong and then they would fade away, and hopefully by then another spark would happen and re-excite the circuit. This was a noisy, horrible way to communicate, but it was also magic because it was the first way we learned how to use radio. If you want to learn more about the very early days, the book I referenced down in the lower left was written in 1936 by a gentleman that lived through the era of spark and the transition to crystals and vacuum tubes and modern technology. So the vacuum tube came along, and by the year 1920 was actually quite common. They realized they could use the vacuum tube to amplify a weak signal into a stronger signal, which of course is a pretty cool thing. What they also noticed is if they feed back a little the output of the tube to the input, they could make the circuit oscillate and produce the famous sine wave. They could make the sine wave relatively stable, more stable than the spark gap. And it would be a very narrow band signal, which of course is very helpful when a lot of people want to use radio at the same time. By 1920, someone realized that you can grind a quartz crystal, place it in the tube circuit, and make the circuit oscillate at an exact frequency. This was an amazing development. Now we wouldn't specify the meter band we were on. We could actually give you the exact frequency we were going to be on, so you know what frequency you could be on and not bother us. So the signal generated, as I said, was and is a sine wave. It's a very high frequency sine wave. RF is more or less considered to start at about 30 to 40 kilohertz and go all the way into the millions of megahertz. Now, when it comes to ham radio, we use CW to send Morse code. Here I'm sending a short burst and a long burst. That's the letter A. Now, why you would call something interrupted like this continuous wave goes back to that thing about spark. Spark generated unstable clumps, if you will, of RF waves. The oscillators, using crystals and tubes or crystals and transistors, generate a continuous wave as long as you keep the transmitter keyed. So in that regard, this is an interrupted continuous wave, so ham operators call it CW for continuous wave. And one last point when I'm interrupting that carrier wave with Morse code dits and das, I'm technically modulating the carrier by turning it on and off. Now you might think, well, that's just turning it on and off. Well, it is, but remember, modulation is any form of putting information on the CW carrier. So CW, as in Morse code CW in ham radio, is considered modulation. But what about AM? What is it? Well, you saw before that we can turn the carrier on and off and refer to that as modulation. But it's very limited. We can't send anything but an on or an off. If we look at the signal, as I said before, it's a high frequency signal. Let's look at it a little different way. Let's set the frequency at several megahertz, so high that we can't see the individual waves. So they look like a wall of blue. So think of this on the right as such high frequency sine waves that you can't even see each individual sine wave. Here's a graph on an oscilloscope screen of my human voice coming out of a microphone on the microphone lead. If we could impose that on the CW carrier and adjust the amplitude or the power level of the carrier in sync with my voice, we would be amplitude modulating the carrier. This is a very simple little transmitter someone might build. The oscillator is a tube circuit generating the continuous wave or carrier wave. The power amplifier is going to amplify it to 100 watts. The microphone in the lower left is going to feed the little speech amplifier, which will amplify that signal to a few volts. The modulator takes those few volts and produces a gain so great that it outputs 50 watts of audio to the power amp. So now I have a 100 watt carrier with 50 watts of audio to modulate it. This 50 watts of audio is going to help the carrier know what level to be at from instant to instant. At times the carrier level is going to get much higher, other times it's going to get much lower than its CW level. This is my monitor scope in my ham shack. I have not keyed the radio. Now I've keyed the radio. That fat green bar is a representation of the voltage of the RF wave on the coax cable leaving the antenna. Now I'm speaking into the microphone. Notice that essentially the voltage level on the coax has doubled. But you can't really see it because my camera isn't fast enough to catch it. But at times, the carrier is disappearing. The power is going to almost zero. So at times, the power level is much higher. Other times, it's very low. Now, watch it in live action. I want to make sure that this is understood.
1, 2, 3, 4, 5.
Let's watch it again.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
If you noticed that that part of the wave that I've outlined in black, of course in this cartoon is a sine wave. My voice is a long way from a sine wave. But the point is, if you follow the curves of the peaks and valleys, it is a depiction of my human voice. And it's only there because we are varying the power or the amplitude of the signal in synchronization with my voice. The next thing we must talk about is power levels, because clearly in AM, the power of the CW carrier isn't steady. it might have a reference level, but when you start speaking, the power level of the carrier is all over the place, from almost 0 watts to twice the power, or maybe even more, of the original carrier. So let's look at the math. Now, you can pretty much forget the formula on the right. Let's look at the one on the left. Notice as the voltage goes up, if you hold the resistance steady, which of course we do, the coax is 50 ohms, the antenna is 50 ohms. If you increase the voltage, the power level goes up faster than the voltage. We say it goes up to the square of the voltage. So obviously on the peaks, the power level is increasing. In the valleys, it's decreasing. But how much does the power increase over the CW or dead carrier power? We can mathematically figure that out, and it's actually very simple. If line 1, the dead carrier or CW power, was producing 35 volts on the coax cable, the math tells us we have essentially 25 watts. If the voltage doubles, which it appeared it was doing on my oscilloscope screen, if it doubles to 70 volts because of that squaring function, I now have 100 watts. I would say my peak envelope power on AM is 100 watts. Now, if you're a ham operator, you probably already caught something. Now you understand why your HF radio is rated for 100 watts, CW, sideband, and FM, but only 25 watts AM. It's because 25 watts AM carrier is all you can get, because when you add the modulation, you're going to increase your power level, your carrier power level, up to 4 times. If you had a 100 watt AM carrier and tried to modulate it, all you would get would be the downward peaks. Your watt meter would show a reduction in power on voice, which you don't want to see, and your audio quality would be absolutely horrible. Now, what I just showed you was a way to look at the AM wave by looking at the envelope, the power envelope. That's because the power amplifier is essentially being throttled or controlled by the power coming from the modulator. The modulator is telling it to ramp up higher power or drop to lower power. This isn't too hard to understand. You can see that on the upper side and lower side, there's a mirror image of that modulating wave. They both are the same wave, just opposite polarity. They have the same information. But the thing is, the PA is doing something else that isn't readily obvious. The PA is acting like a mixer. Let's start out at 7.2 megahertz in the middle of the 40 meter amateur band. Before I put voice in, how about if I just put a 1000 hertz tone into my microphone? What's going to happen is I'm going to end up, in effect, with 2 more signals. I'm going to have the 7.2 megahertz signal plus the 1 kilohertz signal, and I'm going to have the 7.2 megahertz signal minus the 1 kilohertz signal. So I'm going to actually have what looks like 3 signals. In fact, they actually are 3 signals. Now, if I used my human voice instead of a 1000 cycle tone, well, my transmitter limits my microphone response from about 300 hertz to something in the order of 2700 to 3000 hertz, because that's where most of the energy of the human voice is. And if we limit it that much, we take up less of the spectrum, so more of us can use the radio spectrum at the same time. So the human voice might just modulate at something like this. Now, the reason there's a slope to those triangles is the farther out you get, our higher frequencies of our voice generally don't convey a whole lot of power or information unless you use a lot of audio processing. So this slope isn't really real. It doesn't necessarily apply. It's theoretical, but it's one thing in theory that doesn't really work out. If you use a high fidelity audio mixer between your microphone and your radio that emphasizes the higher frequencies up toward 3000 hertz, the slope won't look like this at all. And that's okay. That's fine. So we have two ways of looking at what's happening. It seems like the most obvious one is to look at it as an envelope and look at the peak and not so peak power of the modulation envelope. The other way to look at it is on an RF spectrum analyzer, which is what the lower picture depicts. So we've talked about modulation. What happens at the receiver? Well, at the receiver, we demodulate. In other words, we pull the modulation out of the carrier and send it to a speaker. There's a couple of ways of looking at this. You can look at it mathematically if you want. You could say, for upper sideband, take the upper sideband, subtract the carrier, and you have the audio that you started with. Or take the carrier, subtract the lower sideband, and you have the audio that you started with. Now, those of you that are really familiar with the receiver design, particularly the older designs, know this isn't exactly what the radio receiver is doing. It's looking at the carrier, and it picks, that is, the engineer designs the receiver to either decode the upper sideband or the lower sideband. One of the two. Because they're both the same, we don't care which one. The receiver passes the signal through a filter where, on the one hand, it filters the RF energy out, leaving only audio. But it does this through a tricky combination of comparing the contents of one sideband with the carrier. So if you have a signal at 7.2003, you beat it against the 7.2 carrier. The difference is 300 cycles. You pass that to the speaker. So it's kind of hard to describe what the receiver is doing, but just remember that the receiver's job is to extract the modulation from the carrier. That's as far as we're going to go with this video. In the next video, I want to talk about single sideband. As you've probably guessed, we can't really explore single sideband without taking an even closer look at AM, which we'll do in the next video. Once we get done with that, we'll move on to FM, and then after that, we can move on to the digital modes like DMR, or P25, or Fusion, or D-Star. Thanks for watching. I hope this was helpful, and I'll see you next time.